kind of like some fun applications. Okay, so let's do some applications. Okay, so let A be an R algebra. And I just want to remind you, this is a ring, right? So an R algebra, so A is a ring. Okay, let me just kind of do this on the side again. A is an R algebra. What does an R algebra mean? Again, just as a reminder, that means A is a ring equipped with a ring homomorphism R to A. Okay, and the example that you want to think about, the main example is, A looks like R adjoins some variables, mod and ideal. Okay, so that's what it means to be an R algebra. Okay.
What's the is there a regular or normal homomorphism with that example, or is it
like what are the morphisms in this category?
Yeah.
Yeah, so the category here is, so I write this category is C ring R. And then if you have two of these guys, so a morphism looks like this. So they're F's such that this diagram commutes. Okay, so this is a morphism of our algebras. It's a good question. Yeah, so like every time you see a category, you should always be asking, okay, what are the morphisms? Okay, what are the morphisms? Right. Yeah, so these are the morphisms. So you just need it to be, so this is like R linear, right? R linear ring homomorphisms. Okay. Okay, so let A be an R algebra. Okay, so there's this there's two functors that we can do. Okay, so we have two functors. There's the first functor is restriction of scalars. Right? Okay, so the restriction of scalars, it's a functor from modules over A to modules over R. Right? So how could you define this? Can someone think about how to define this? And it's really stupid, right? And so all you do is, this is the module M viewed as an R module through this ring map R to A. So we know we have scalar multiplication by A on this module because it's an A module. And so what we do is we just take the element of R, we stick it into A, and then we multiply by it. Okay, but we're only going to use the R multiplication. Okay, so this is restriction of scalars. Okay, and then there's the other one, which is base change or extension of scalars. Extension of scalars. Okay, so this is one that comes up. So this thing is that you have a map from, you have another map. Okay, and I can take an R module. I can take an R module and I can turn it into an A module. So how can I take an R module and turn it into an A module? Well, I take my module, right? And let's call this N maybe. N here. Okay, and what I'll do is I'll map it to A tensor over R with N. Okay, so what I did is I just tacked on an extra factor, and so the multiplication here. So the A module structure is given by something like so A, and if I wanted to multiply, let's just do it for simple tensors. A1 tensor N1. Well, this is going to be defined to be AA1 tensor N1, and this is over R, I guess. Okay, so you just kind of multiply in the first factor. Okay, and so what does this do? So it allows us to like take R modules and turn them into A modules. Okay, so I just threw down two functors. Okay, so maybe I can give an example. Let me give an example for both of these too. So let's give it examples. Okay, so like, so you know, let's take C. So C is an R algebra. Okay, so and then what we can do is we can take M is equal to C, then MR, right? So this is a C module. Let's just C to the N, why not? Okay, MR is viewing C to the N as an R vector space. Okay, so that's what restriction of scalars is. Okay, so okay, so this is one. Okay, and then what we can do is if V is an R vector space, then so we can, what we do is we take the base change. So what this is so this is the new vector space, same vector space, but with complex coefficients. Okay, so what we did is we took we took a real vector space and we can turn it into a complex vector space. And if we have a complex vector space, we can turn it into a real vector space. But this is like totally general, and it goes with modules. Okay, and so I just introduced two functors: the base change or extension of scalars functor, and then we have the restriction of scalars functor. And so what am I going to tell you? I'm going to tell you that these are adjoint functors. All right. Okay, so exercise. Okay, so show that that restriction. Let's do it this way. I'm going to do this extension and restriction is an adjoint pair of functors. Okay, and by that I mean we have this. What did we tensor? We tensored n first. I just want to keep the notation kind of consistent. So morphisms from something that's tensored up. Well, let's keep the notation completely the same. A here, M. This is naturally isomorphic to N MR. Okay, so we have this this adjunction here, so that extension of scalars is the left adjoint of restriction of scalars. Okay, and the way to do this is just the usual tensor the biring thing. Okay, so this is not biring. Sorry, not biring. I'm bimodule, right? So I made this comment about associativity when you have two, when you view a module as like a left module by something and a right module by something. And this is one of those cases where like we can view, A as a left A module and a right R module or something like that. Okay. So yeah, so that's all I want to say about that. So we talked about reduction mod P. Okay, so let me give some stuff with geometry now.